I'm Norman Wildberger. Today we're going to talk about some triangle centers and how to think about them using rational trigonometry. The most important triangle center is probably the circumcenter. It's obtained by taking the three perpendicular bisectors of a triangle and intersecting them. So let's have a look what that means. Here's a side of a triangle, and there's the midpoint, the point that's equiquadrants to each of the points. The line perpendicular to the line segment through that midpoint is called the perpendicular bisector of that side. And it has the property that any point on it has equal quadrances to A1 and A2. So if we take two such perpendicular bisectors, say that one there and that one there, then the intersection point there, called C, has the property that its quadrants here to here is equal, and its quadrants here to here is equal. That means that its quadrants from here and to here are also equal, and so it must be on the third perpendicular bisector of the last side. That's a relatively simple reason why the three perpendicular bisectors all intersect. And this circumcenter, the point of intersection, has the important property that the quadrants to each of the three points of the triangle are equal. We're going to call that equal quadrants K, the circumquadrants of the triangle. And an important question will be for us, how do you calculate that circumquadrants K in terms of the quadrances of the original triangle? To answer that, let's go to the second triangle center, the orthocenter. Here's the same triangle that we're interested in, A1, A2, A3, and now we consider the three altitudes of the triangle. An altitude is a line through a point which is perpendicular to the opposite side. There's one altitude, there's another altitude, and there's a third altitude, and lo and behold, they all intersect at a point. No matter what triangle you choose, they always intersect. This was actually one of Albert Einstein's favorite theorems in geometry. The proof that we're going to show you goes back to Carl Friedrich Gauss. What we do is we construct another triangle, a bigger triangle, going through the 3 points with sides parallel to the opposite side. So through A1 we draw a line which is parallel to A2, A3. And similarly through A3 and A3, A2, lines parallel to these ones. Now this bigger triangle turns out to be similar to the original triangle simply because of those parallel lines condition. But it has another important property that we can see by looking at some parallelograms that appear. So have a look at this parallelogram right here through these 4 points. It's a parallelogram because the opposite sides are parallel. That means that this quadrant here, which is called Q1, must be equal to this quadrant here. And now we're going to say the same thing for this parallelogram. All right. It also has equal opposite sides, so this side here, which is Q1, must also be equal to this side, which is Q1. And so that means that this is a midpoint of that side. And therefore the line that we originally drew as an altitude of the small triangle is actually a perpendicular bisector of the larger one. And so that point there is the intersection of the 3 perpendicular bisectors of the big triangle from the first observation that we made. So the orthocenter of A1, A2, A3 is the circumcenter of B1, B2, B3. And we make one more additional interesting point, that because this triangle B1, B2, B3 is twice the size of the A1, A2, A3, this quadrant here from its circumcenter to here must be 4 times the circumquadrants of the triangle A1, A2, A3, namely K. Right? So that's 4K. All right, let's have a better look at this orthocenter situation. So here's the triangle A1, A2, A3, and there's the intersection of the 3 altitudes. Because we have a lot of right triangles involved here, it's actually easy to analyze the situation and find all the spreads and all the quadrances. So how does that work? In this triangle here, A1, A2, F1, which is a right triangle there, this spread is S2. That means that this complementary spread must be 1 minus S2. And because this quadrant is Q3, and that spread is 1 minus S2, this quadrant here divided by Q3 must be this spread, telling us that the quadrants between A2 and F1 is Q3 times 1 minus S2. In a similar way, the quadrants between A3 and F1 is Q2 times 1 minus S3, and the quadrants between A1 and F3 right down here is Q2 times 1 minus S1. So these are all three very much similar. Let's take this last one here, so we know this quadrant's here, and try to find the quadrants from A1 to O using that. First we make the observation that we have another right triangle here. That spread is 1 minus S2, so that spread there must be S2. And S2 is this quadrant divided by this new quadrant. And so the quadrants between A1 and A0 is the quadrants we've just found, A1 and F3, divided by S2. So there's the expression. That one there divided by S2. Now let's have a look at this expression here. Q2 over S2 can be replaced using the spread law by Q1 over S1. And that allows you to simplify things because these S1s kind of cancel, and we get Q1 over S1 minus Q1. That's an expression for the quadrants between A1 and the orthocenter O. Now let's go back to the previous diagram over here. We've just now calculated that in terms of the quadrants and spreads of this triangle A1, A2, A3, this quadrant here is Q1 over S1 minus Q1. Now have a look at this right triangle right here. We've already earlier decided this one is Q1. Now that's Q1, and that's Q1 over S1 minus Q1. And when we add them together in Pythagoras' theorem, we just get Q1 over S1, telling us that 4K equals Q1 over S1. That allows us to rewrite the spread law in an extended form. So here's the spread law in its usual form. S1 over Q1 equals S2 over Q2 equals S3 over Q3. We've already established this formula for it in terms of the quadrant. Now we can see that its common ratio is also 1 over 4K, where K is the circumquadrants of the triangle. This is the extended spread law, and it's an important relationship for circles that we'll see later on. Notice that it allows us to write K as a ratio of the product of the three quadrances divided by the quadria. So the third point that we want to consider is the centroid of the triangle, and it's obtained by taking the three medians. A median is a line joining a point of the triangle to the midpoint of the opposite side. There are three medians, and they intersect in any triangle in a point called the centroid. One way of seeing that is using a physical argument. It goes back to Archimedes. If you imagine a transparent plastic triangle with very little mass, and then putting three larger equal masses right at those vertices, then this triangle will balance exactly at that point G. And the reason is because these 2 points here themselves balance at M1, and so this is a line of balance for the entire triangle. Similarly, that's a line of balance, and that's a line of balance, so all three lines must intersect at the common center of balance. We would like to understand this in a little bit more general way, though. This is not exactly a satisfactory explanation, so we're going to develop next time a theory that allows us to consider not just this kind of situation, but something more general like this, where we've split this side into 2 equal pieces, and we split this side into 3 equal pieces. And we've drawn these lines from the vertices, and we would like to know what happens if we draw this line here. What is the ratio between the 2 quadrants here? So we're going to establish a theory that describes this kind of situation called the law of proportions, and then we're going to use that to establish that the centroid really exists using this theory of proportions. So I hope you'll join me for that. I'm Norm Wildberger. Thanks for listening.